Hello. Hello, everyone. Let's give it a minute for people to get the notification and stream in. Just posting on Blue Sky and Mastodon. All right. All right, there's already someone. So, how's audio? How's video? How's the font? I haven't streamed in a hot minute, so if there's anything worth changing, now is a good time. Excellent, thank you. All right. So, um, ML-DSA. ML-DSA. It's signature algorithm. So we're going to be implementing key generation, formats for the public and private key, and we'll implement signing and maybe verification. It's based on module lattices, so it's a post-quantum signature algorithm. It's kind of similar to ML-Chem, so if you've read the article about the math needed to implement ML-Chem, you already have everything. It's actually not that much. So let me pull up a guest profile here. I wrote up a lot of what's needed to know for the math and the polynomials and the linear algebra in this article, and I went back yesterday and added a little section for how ML-DSA is different. It's not that different. So fundamentally, we're always dealing with integers modulo this prime, which is what I have already implemented here. A field element is a value between 0 and q. We're operating on them in the Montgomery domain, which is just a way to do faster multiplication with reduction. But basically just means that instead of saving them as instead of saving a value n, we save n times r, where r is 2 to the 32, and then that makes it much easier to do reductions because it lets us replace one of the divisions with a shift by 32 bits, which, if you think about it, if you take a uint64 and shift it by 32 bits, you're just taking the top 32 bits, and it's very easy. Then we have polynomials. Polynomials, for our purposes, are just 256 of these elements, so 256 coefficients. Each of these parts of the polynomial is a coefficient of a different value. The actual polynomial looks like this, but actually we don't care that much. Because the spec gives us all of the stuff we need to know. Then there's the NTT, which is more efficient representation for, again, the polynomials. It's the same as the Montgomery representation. Like the Montgomery representation is a easier form to multiply two values modulo q in. The NTT transform is a easier form to multiply two polynomials. To the point that multiplying two polynomials is just multiplying, literally multiplying each coefficient and saving the result in the corresponding coefficient. There's some vectors and matrices. These are nothing else than arrays of fixed length, and the length is the one you see in the parameter of ML-DSA. So if you ever wonder why ML-DSA has these weird parameter sets, 44, 65, 87, instead of, I don't know, 1024, 512, and so on, it's because this is K and this is L. So these are this is the size of the matrix and of the vectors that we multiply by the matrix. No, you truly don't need that much math. We really get to treat almost everything as just an array of a bunch of uint32s. Then what else? Oh, and then there's this annoying thing of the infinity norm, which we'll get to when we need to get to it. But really, an interesting thing about ML-Chem and ML-DSA, which is the point of this article, is that actually there is very little math in implementing them. You need to understand more math to implement elliptic curves than you do to implement this. Well, I guess it depends. If you have an article like this, you could probably also summarize the math needed for elliptic curves. Maybe another day. Okay. Let's start with key generation. So I already have, as I said, just implementation of the field and a couple types for the polynomials. The ring element is, again, just 256 field elements, and the entity element is also 256 field elements. We just have different types so that we can't, by mistake, try to multiply something that's not in the entity form. While addition and subtraction are generic because this way they can apply to both ring element and entity element, because addition and subtraction works the same for both of them. Also, let me just close some extra windows so I can always see the chat. Okay. A question from chat is, does the choice of representation like Montgomery have an impact on constant time requirements? Yes. So really you can't do, these are small numbers, so you could just implement things using percent, and for example, in the tests, to check that my code is right, I just do percent %q because we're operating modulo q, and so I just do a times b, I put them in uint64 so they will fit because q is 23 bits, so it will overflow a uint32 if you multiply two of them. And then we do percent %q. Now, this, though, is a division instruction on the CPU. Division is not always constant time. This was a whole thing in the reference implementation of ML-Chem. We had it right because in the ML-Chem field, we use a thing called Barrett reduction, which operates on the regular representation, like takes the actual values. It's a little slower. It's a little slower per multiplication, while Montgomery reduction has a bit slower getting in and out of the Montgomery representation, because you have to convert to and from the representation, but then you get to do faster multiplication. But yeah, both Barrett and Montgomery let us do reduction without using the division instruction, which is the one that is variable time and could leak pieces of the secret, because the values that are passed here might be secret. So the time it takes to divide them or to take their modulo, like I do in the tests, the time of this operation could leak secrets. So instead, we just do multiplications, additions, shifts, which are all constant time. Hey man. Cool. Now, so we have a few types here. I'm wondering if we should take it from the top. So from the highest level functions and the data types, or take it from the bottom, implement the smaller functions. Let's try taking it from the top. So key generation takes, all right, I clicked something. Key generation takes a 32-byte seed and expands it with shake 256 into a few other values. So we're going to need those other values in our private key type. So let's start. We'll add a new file in ML-DSA. Package MLCam. Oops. I copy pasted the initial field implementation. Okay, so we said we'll make a type private key. And the private key will be a struct with, we're going to keep the seed, which is 32-byte, because we might want to reserialize it to export the key. We're going to public random seed using the seed, a polynomial matrix. Okay, so this is the seed that is used to expand the matrix A, which instead we're just going to save the matrix A. Now, the problem of matrix A is that its size depends on the type of the parameters that we talked about earlier. It's either, where is it? It's either 4x4, 6x5, or 8x7. We could just make it 8x7 in the struct and then use only a part of it based on the parameters. So we're going to need K and L, which are the parameters. Are they defined in here? Here, K and L, dimensions of A. Yeah, let's define some constants for the maximum K and the maximum L, which are 8 and 7 respectively, so that we can make A max K by max L list of field elements. Then, what else is in our key? A private random seed. Using the seed, the polynomial vectors s1 and s2 are pseudo-randomly sampled. So instead, we're just going to save s1 and s2. S1 and S2 are in R. They're vectors, one of length L, one of length K, of values of polynomials. That's RQ. So S1 is going to be, yeah, max L of, oh, these are not field elements, these are polynomials. So what's the type of the polynomial? Ring element. And S2 is that. Okay, Okay, so these will have to generate pseudo-randomly like the spec says. And then a 32 private random seed K for use during signing. Okay, that one we can just save. I think this is probably all we need in an expanded form, and this we can rebuild the regional private key from, and this we can use for signing. Right, now, private key, what methods should we have on private key? Let's see. Let's look at the ED2509 private key type. It has equal, we should probably have that. It has public, which we should have because it's defined here. Private key is unfortunately empty interface, but we say you can assume it will also implement these methods. So one is equal, the other is let's call this p. Well, nah, prev is fine. And the other one is we said public that returns to public key, and then we're going to need so this has seed, but that's because there was debate on what was the private key and what was a seed, which guess what is also a damn debate in for ML-DSA, because NIST defined an encoding for private keys, which is neither the seed, which is the compact, safe one that can't be invalid because it's 32 bytes and you expand it into all the other values, nor the stuff you actually need, because, for example, it doesn't include the A. It has this format which is like an encoding of this and this and this and I think something else. I hate it because it means you have to actually check that these are valid ring elements, and it introduces the concept of an invalid private key without at the same time being a useful in-memory representation. It's a semi-expanded, which is neither here nor there. I hate it. So we're not going to implement that. Instead, we're going to implement, we're just going to consider the seed bytes. Although I need to check how we did it for MLChem, because unfortunately we need to support here testing only expanded bytes is the one that returns. Okay, so okay, bytes must not be called on the return key as it will not produce the original seed. Okay, and we put a random value in the seed just to make return something. Okay, so we'll do the same thing. We'll say that the silly interface that nobody wants is the testing only interface, which is needed to pass NIST test, whatever. Okay, so I think this is it, and then we're going to implement signer, which is this here. What the signer ops are going to be is actually going to be one of the most interesting parts. But we're getting ahead of ourselves. Let's do key generation first. So equal is reasonably easy. So if it's not a private key, it's not. And then if it's just a matter of is it? Yep. It's just a matter of comparing the two seeds. And we do that in constant time just to be safe. If the seed is the same, everything else has to be the same. Again, if we use seeds, but why would we not use seeds? Public, we are not there yet, so we're just going to panic unimplement it. And bytes instead is easy. Bytes.clone of priv.seed. There we go. And this will get inlined into the color, so there's a chance for clone, I think, to keep the value on the stack. Maybe. I'm not sure this will... Well, at the end we'll do a test that checks allocations, and we'll call a bunch of functions, including bytes, and we'll check that it doesn't allocate unintentionally. Okay. Now, the actual key generation, which is func new private key, which takes a seed, and we've got to decide how we specify the parameters. We could just have 3 functions. New ML-DSA 4.4. There's a question, is there an IST requirement to get a key into a private key struct without a seed? So yes, they, well, in order to get FIPS on 43 certified, you have to go through the CMVP. The CMVP includes testing modules using including the CAVP, which is the cryptographic algorithm validation program. That requires you to run the automatic cryptographic verification protocol, something like that, which is essentially just a bunch of test vectors. Let's skip the FIPS details. And the test vectors give you the private key without the seed, because they give you the semi-expanded key, and then they ask you to do a bunch of signatures and stuff with it. So we're going to expose, like in like we did in ML-Chem, a testing only new decapsulation key. Well, it would be a testing only new private key, which will not expose. This is an internal package, and we're going to use it for ACVP testing. I don't love it. It is what it is. All right, so we could do a enum. We could do a enum, or we could do separate functions. When would you want ever to support different sizes in the same call site? I think generally I want to discourage that. I want to encourage folks to pick the size that they're comfortable at, which for ML-DSA is not clear. For ML-Chem, it should be 768. For ML-DSA, depends what you're doing with it, but that's kind of why we're not exposing an interface publicly yet. We don't know what to recommend to people yet. Let's do separate functions. So that's going to be new private key 44. And seed is a byte slice, and it returns an error. Not that there's any value that can error out, but I always prefer taking a slice and checking the length myself instead of causing panics. And then here we call return new private key seed 44, and I'm sure it can imagine. It cannot. 68, is that right? Parameter sets. Nope. 65 and 87. Eight seven is right. Okay. Okay. So we've got the the types, we have to, well, we start getting our hands dirty. So I think keygen, there's an external function which is actually very uninteresting. It's just saying if you're going to do key generation, just sample 32 random bytes and then return those, which, duh, yep. Let's go copy whatever we did for generate key here. It uses drbg.read directly, and then it has a lot of this 140 craft that you don't care about, and has some outlining to avoid allocations, but we're going to do that optimization later too. So generate key is nothing else than not taking rand, and instead it's going to be seed drbg that one dot read seed. It does not return an error because if it were to fail, it would just explode the program. But also it never fails. Okay. Okay, so that's the external part. Now let's get to the interesting part, which is the internal key generation. So it takes a seed, and the seed is that, whatever. It splits. No, okay, it calls H, which is defined as, I think, shake 256, while G is shake here. It's shake 256, so we make a new shake 256 and we call it, let's pick that letter, SHA-3, the internal one, that one dot new shake 256. We write the seed, and then we expand. And we write also K and L, so that if you use the same seed with two different size of keys, which you shouldn't do, it will generate independent things anyway. So that's going to be byte of, well, K and L ints. Yeah, let's keep them as ints. Byte K, byte L. In that order, yes. Okay, so then we generate, is that faux? God, I should learn. What is faux1 used for? Okay, so this is another seed. So it generates a few seeds, of which only one then actually needs to be kept around. Except you see here here is the stuff that actually it saves, which truly there's no need to save it in this form. For example, it saves in the private key encoding the lower bits it has just discarded from T, which instead could just save T, which it will need. So instead, every time you make a signature, it reconstructs T from A, S1, and S2. No. Anyway. So T is going to be the size of S2. So T and S2 we gotta save, and there says K. There. Raw. Thank you. Integer to bytes, does the byte order matter? It does, but in this case it's only one byte. So it's just the value. Okay, so we can generate them 32, 64, and 32. We said 32, and I never know how to call the things primed, but so we said that one is 32 and the other is 64. And we read first that, then that, and then we read, so priv is a private key, and finally we read okay, there we go. So yep, that's expansion. We have to do the expansion of A, I think. So that's going to be our first internal thing to do. Let's open it in a new tab. That did not work. Samples a K by L matrix A of elements of DQ. So to save time on sampling the matrix, which is a lot of the runtime of the algorithm, which I always thought they could have just hard-coded the matrix because it doesn't have to be different between keys. But I think they like the whole reason we do all of this complexity and all of this CPU is politics, optics. Like people already say, and when I say people, I mean a certain person in particular, they say, oh, the NSA is intentionally making people, and especially the US government, use weak stuff, which I won't even get started on the logic of the NSA is forcing the US government to move to weak stuff. Not backdoor stuff, but weak, which is very different. But anyway, the matrix is generated on the fly every time, specifically so that there isn't a hard-coded value that could be a backdoor. Anyway, we have to do all of this work just to avoid allegations of backdoors. End of rant. Does error new cache values, or do you allocate a new error every time? So people sometimes ask this and like send CLs to make it return a fixed value instead. But I always felt like allocating only matters in the happy path. You're probably not doing a million attempts at generating a private key from a seed of the wrong length. I don't know. If I'm wrong, we can always make it fixed values. Just, you know, I never understood the need to make the error path more efficient. Okay, so we go R to K, S to L. We concatenate for row with S and R, and then we do reject entity poly, which is another call of shake. Okay, there's a lot of shake. I guess key generation speed in ML-DSA doesn't actually matter. It matters in ML-Chem because you're constantly generating new keys. Comparability, fair enough. Yeah, we can always var there. Yep. So yeah, in ML-Chem, the speed of key generation matters. Here it does not. So first, to be able to implement this, we need to implement this. And reject entity poly. What does it do? It instantiates a shake 128, not a shake 56. It puts raw into it. it squeezes 3 bytes. It generates a coefficient from those 3 bytes. Then, and if it fails, it just squeezes 3 more bytes. While instead, if it succeeds, which this one is just a fancy way of saying if error equal nil, it moves to the next one, and it just keeps doing this. Okay, coefficient from 3 bytes is not clickable. Why is it not clickable? What? Nothing about page 29 is clickable. Okay. All right, there it is. Algorithms 14 and 16 translate byte strings into coefficients of polynomials in R. Coefficient of 3 bytes is a 3-byte string to either generate an element or return a blank symbol. Okay, so that's just parsing 3 bytes into a polynomial, and I think, what does it do? It sets the top bit to 0, because 3 bytes are going to be 24 bits. We need 23 bits, so it just clears the top. The top makes sense. And then it just interprets it in what looks like big endian. Yeah, that's big endian. Big endian. And then checks if it's higher or lower. We already have a function to check if something is higher or lower, which is field to Montgomery, which already does the comparison for us. And that one, it's okay to not be constant time in rejecting things. Let's figure out if coef from 3 bytes is used anywhere else than the stuff we're implementing, because if it's not, we're just going to inline it. Yeah, it's not. So let's just implement reg ntt poly, and we can put it in field. I think we had something similar in here, so I want to just name things consistently. I think it's the same as sample entity. Yep. Yeah, it's different because the MLChem has smaller values, but it's essentially the same. Yeah, they described it differently, but it's actually the same. So let's implement that with the same name. So we're going to have raw, and then if we go to look at where this is used, we'll see that actually the raw that's passed in, come on, it's not that big of a PDF. Yeah, it's actually raw prime, and raw is the concatenation of raw, S, and R. So let's just have S and R in here as bytes. And it always returns an entity element. So same thing. It starts by it's first raw, then S, then R. And S, then R. Very annoying that they describe things differently in these two specs published by the same people for algorithms that are obviously going to get implemented by a lot of the same people. But okay. So we do ginit, gabsorb, the new raw, which is actually the concatenated one, And then for each we do that squeezing and rejection sampling. Let's just copy the scaffolding from here. It's going to be essentially the same, except it's one thing at a time instead of two. How do they call the context? They call it context. Okay, we're going to call it B. I lost track of the chat. Is the while loop guaranteed to terminate? Yes, it is, because every sampling is from a uniform distribution, so every sampling has a pretty decent probability, actually a very high probability of falling in the of not rejecting. So if you keep running, it will, because you're squeezing from a shake, which is uniform, and you're checking if something is lower than this value, which is 2 to the 32 minus 2 to the 13 plus 1. So the chance of reject, and we're clearing the top bit. So the chance of rejecting is only if it's higher than this, but at the same time, lower or equal lower than 2 to the 24. There's actually very little space in the middle there. So we'll actually have to be a little careful to test it. Yep. Okay. So we've got our entity element, we've got the J index into A. Buffered reads from B. If it turns out to be a performance issue, we can probably do multiple of these at a time. But for now, let's just have a buffer of 3. Oh no, we had done exactly that. So the offset starts at consumed. If the offset is consumed, then we read a new buffer. Okay, and then this is the actual yep, which we need to. So we can simplify it a bit, because the last one was for j less than n. And we do this algorithm here. So we squeeze 3 bytes. Oh no, sorry. We already have the 3 bytes from the buffer, although it needs to be a multiple of 3. So let's pick, I don't know, 27. Let's just do 30, which is clearly a multiple of 3. Our potential value here, it calls it S, but we already have a S. Oh, come on. V it is. And we wanted big endian, I think. That's what coefficient from 3 bytes was doing. Right, coefficient from 3 bytes, which we need to jump to by searching. Yeah, I agree that ML-DSA key generation will not be significant. ML-Chem key generation is significant, which is why all of this code is so optimized. And I guess, to be fair, this is actually matrix sampling is used in verification too, so we do need to make this one efficient. Okay, so oh no, wait, this is little endian, because B0 is the least significant, then B1, and then B2. They just put them in the order. So 0, 1, and 2 shifted. Yeah, that's right. We consume the offset, and then ER is field to Montgomery of the 23 bits. Set the top bit to 0. Yep. Which, yeah, we can do with the end there. I think that's fine. Yeah. I prefer seeing it, so it's going to be that's going to be 0, 0, 0, 0. Wait. 0, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. Okay, maybe this was a bad idea. Yeah, that's not more readable. But if we remove this and this and this, that might be decently readable. Yep. Okay, so if error different from nil, continue. And otherwise we return the value, which returns to here, which just increases j and moves to the next one. Wait, no, we also need to set that, right? Okay, I think that's it. Let's call this f. And I think this is sample entity. We can document it. Sample an entity element uniformly. Set row. Yep, it implements. Well, it implements from the top. Project entity poly and coefficient from 3 bytes. Folding, passing in the where is it? Passing in row S and R instead of row prime. Okay, so we have that. We can do expand A. And expand A. Should we just do it in line? Let's see how long it is to do it in line. So this is the first part where we just did this, and then A is just expand A of raw, and expand A takes raw and uses it as is plus those indexes we were talking about. So it's going to be R range K S range R and prev A R times L, yes, plus S, yes, sample entity byte R byte S. Yep. Well, maybe no. Oh, A is a entity. See, types, useful. Okay, so I think that's it for expansion of A. Cool. Any questions up to this point? Did I miss anything in chat? I don't think I did, but next we've got expand S, for which we use the other annoyingly named seed, which I'm actually going to rename raw S, because it's the one to generate S. All right, let's close some tabs and then duplicate it and then go to what? Okay. Samples vectors S1 and S2, each with polynomial coordinates whose coefficients are in the interval. Okay. So they're the same. Again, we have the seed concatenated with an integer, which this time is a 2-byte value, so a uint16. Goes from 0 to L minus 1. Why is it 2 bytes? And then from 0 to k minus 1, and for them to not what? Oh, for them to not overlap, they add L. Okay, fair enough. Seed depends on R plus L, yes. Wait, how high does it get? Like, one of them can get at most 8 and the other at most 7. Why are they 2 bytes? The first byte is always going to be at... The second byte is always going to be at 0? This is weird. Page 28, not clickable as ever. Yeah, little engine. Simple little engine. Yeah, R is at most k minus 1 and L plus L, k minus 1 plus L, it's 14. Why 2 bytes? Oh, I bet because this way it's domain separated from the other seed. No, it's not even the same size of seed. All right. Don't need to question it. Let's duplicate and have reject bounded poly. Of course. Okay, what does this one do? So same thing, it takes raw with some concatenated stuff, which we're going to call R. It returns no, wait, I'm looking at the wrong one. It's reject bounded poly. Samples an element in R. Okay, so it's a polynomial, not a No, okay, they're both polynomials. With coefficients in this computed via rejection sampling. Okay. I need to go look up what that parameter is. The private key range, which is 2, 4, or 2. Great. We might need actually a structure somewhere to keep the size of the actual parameters. Yeah, all right, let's do a type for parameters. It has K and L, and it has N in bound for super coefficients. Copilot knows some ML-Chem, which is interesting. Not sure what else we're gonna need for now, but that's fine. And then we're going to have var 446587. See, no sum of it, but 65 has a 4 here. And then instead of passing in K and L, what did we call them? Params 44. Can you rename it? Is it too close to faux? Well, it doesn't have a raw. Oh, come on. Yeah, that's probably fine. I mean, yeah, we could in the future have higher values, but no, not in this document. You can always redefine that function, but also, okay, whatever. Okay, back to us. Where were we? We are going to implement this rejection. Why does it say it's in R and not in RQ? I think those are different. Yeah, it's over. Oh, because right, because they're just 0, 1, 2, 3, 4, right? Because that's what we're going to do here. Our coefficients are going to be in a much smaller range. Okay. Not sure converting them to Montgomery is the most efficient thing, but also this is sampling the private key, so it can be inefficient. Who cares? We're going to just treat them as bring them into the Montgomery domain because why not? Okay, so fun sample bounded poly. It takes a row and it takes a R, which I'm just gonna make it a byte, and if it explodes, then I'll have learned why they don't. So let's go to where rigid bounded poly is called. Remember that it's passed raw, and then that has 2 bytes, and then it passes it to H, which is shake 256. And does it give it a name? Nope. So we're going to call it, well, I guess we can call this one G, and we can call this one H. 256, and it's going to write row, and it's going to write R, and then at 0. Why? Not sure. I'm going to leave a comment because I will wonder in the future. Does it do the same thing? Only advancing J if it found... Yes. Yes. This time we probably don't need to do the buffering because we said it doesn't have to be efficient. However, let's see what it does. It squeezes 1 byte, then it takes it mod 16. Okay, so that's... Okay, so that's masking the bottom and the top bits. And then it calls this coefficient from half byte, which I bet is just comparing to our yeah, there we go. Minus, plus, yeah. Here. Okay. So if it's 2 and b is minus b is less than 15, then return oh god, why is the if nested like this? Then this will not hit, and this is the final. Okay, I hate it. Right, let's write it out. We can't use a switch because that would not be constant time. We have to take the parameters. So we do a switch on the parameters. And we have the case 2 and the case 4. And the default is just panic because we... internal error. Okay, so if it's 2... Mod 5? That does not help. Mod 5 is not constant time, god damn it. Ah! Also, these are negative... I'm sure they found it a lot better from a like specification point of view to just talk about negative numbers, but god, this does not help me. Okay. So I have a field reduced once, so I can... Let's start with the case 4. The case 4 is if b is less than 9, so if b greater or equal than 8, right, we also need to return an error here. Now let's just return a bool. False. From a chat, you can have an array of size 16 with the mod 5 values. Nope, because then you'll be indexing using a secret index into it, and indexing is not constant time. So, all right, what we do here is q plus 4 minus b fair enough and then we do field reduce once of it. I think that's it. Huh, interesting. So looking at the spec, the reason for the 2 bytes in expand s might be copy paste from expand mask in a hurry. I actually can believe that. All right, so wait, this is minus 4. Okay. Okay, I just want to see it in front of me. Wait. 4. So these are 1, 2, 3, 4, 5, 6, 7, 8, 9 values. And I think this is correct, but this is the kind of stuff that I want to really be sure about. Wait. Oh, this is just, see? Haha, there was a good reason to map it out. It says, I hate the ifs in this spec so much. It says if b is less than 9, then it's valid. So if it's higher than 8, off by ones, people, off by ones, you return 4 minus b. Okay. And for 4 minus 0, that's not the mapping, is it? I think 0 is here. Because 4 minus 0 is 0. 4 minus 1 is 3. 2, 4, 5, 6, 7, 8. I think this works. yeah, being able to hover on things in specs would be great. In general, specs could be in a much more usable formats. Okay, so I think this is it, because it says to return 4 minus b. And what does it call the return value? It doesn't give it a name. Okay, maybe what it's called? Z. I'll take Z. Okay, 4 minus 8 minus 4, that looks right. And we do that by doing a conditional subtraction. Yeah, I think that works. The 2 case. The 2 case is b mod 5. Fuck my life. Okay. Which maps from? Okay, I think it fits how many? We said that this is up to 16 because it's half a byte, so it's going to be 3 sequences. And they're again reversed, so it's going to go up to 14, I think. Copilot, you could have figured out this sequence. Copilot is messing with me. All right, is this right? Less than 15, higher than 14. That part is right. So minus 2 mod 5. So mod 5. Let's do 2 steps. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. Okay. Why is it disaligned? There. Okay. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So 2 minus 0, 2, 2 minus 4 minus 2, and then back to 0, 2. Okay, so this is the distribution. Now, how the hell do we do that in constant time? Fucking modulo 5. According to the spec, I don't think b equal 15 is a valid case, because b has to be less than 15 to return. So if b is equal 15, you return this, which is why I say this structure of if is the least readable way to write this out. Oh, integer. Yes. So these are all of the possible values of 4 bits, which is what we take here. We could also just have if b higher than 15, panic, half byte out of range. But then for the value 15, it returns this. It's a valid input, but it returns a rejection. That's the rejection symbol, which is what we call false. Just like here, we return false for above 8. See, this is why spec authors should talk to implementers. I'm almost sure that whatever I'll have to come up with here to be constant time will be slower than just rejecting much more often to only sample 2 of these by just splitting it into 2 bits and 2 bits. Which would have been enough, right? 2 bits has... Oh, no, it does not. It has 4 values, not 5. Well, even if we only sampled 1, just like this case, it would probably have ended up faster anyway. All right. So yeah, thanks for the note about order being important. So we want parents. Oops. There. How do we do this in constant time? I'm actually about to cheat and go look at boring SSL. I don't know. I swear to God. Really? What did you call that? Good to see that they also have Montgomery, and they also used the prime negative inverse with the unsigned integers. The spec goes out of its way of putting appendix in there telling you should do Montgomery. Here is just a ready-made algorithm for Montgomery reduction, which uses signed integers. So it's useless. But it took me even longer to ascertain that I was actually doing the right thing by using a different constant, and the reviewer will have to also look at it and be like, why is your constant different from the one in the spec? Well, uh, we're gonna have to do a lot of annoying stuff for bitpack and bitunpack. Okay, so this is reject entity poly, which it does just like we do. Good. And it also does block. Oh, it does a interesting. Oh, that's a better idea. So shake to 56 has a certain what's it called, rate. Shake 128 actually, which is how many you can essentially squeeze at a time, and we should probably just use that. And that's divisible by 3, right? Yup. Okay, coefficient from nibble 4 and 2, this is it. Yeah, Clang really wants to... wait, mod sub? Huh. Boring SSL just declassifies the nibble and does a module on it. I'm not sure this is fine. This is the private key. I mean, I don't expect it to be exploitable, but it'd be fun if I found that security issue in Boring SSL on stream. Let's look at what mod sub does. It asserts that they're both less than the prime. It does a subtraction. Oh, it's our modular subtraction. It's a minus b modulo. Yeah, it's basically the same as our reduced ones. Actually, we could probably use just sub in our... Wait, we're not converting it to... We're not converting it to Montgomery form. Whoops. My bad. Right. We could use field sub. Or maybe we need a new, better function. Field sub to Montgomery. Because we're kind of... I don't want to cast something to a field element before it's actually a field element. Also, it looks like they don't move it to Montgomery. Right, I'm getting too distracted here. Let's fix the modular subtraction first. It needs to be in Montgomery if we're going to call it a field element. Reduce ones should really be an internal thing. I should not have been using it this way. And arguably should take a field element. No, because field element is also reduced. Okay, so what do we have here? We want to do 4 minus b. Let's make a new function that has smaller bounds. And b here is a byte, so we can use a byte here. Field sub to Montgomery converts a value a difference a minus b to Montgomery form. A and b, we're gonna make them bytes, and then we can drop the error because it will always fit. And to do that, we're going to do the same as sub does. So we're gonna do that. And then I think we can put that straight into Montgomery Mall, because I think Montgomery Mall has wider bounds. I did not write down the bounds for it, but the multiplication then goes into reduce, and reduce has to be less than q times r, and this is going to be way smaller than q times r, even if we don't do this the subtraction, because to do that we multiply it by rr, which is reduced modulo q. So that's the q part of q times r. The other value can be up to r, and our a minus b plus q will never be higher than that. Okay, so we can do field Montgomery reduce, I'm gonna put it here, of or rather field Montgomery mole of x, and x is going to be u in 32a minus b plus q. That sounds about right. There. Okay. So then here we can replace this with for NB. Okay, so that fixed the thing was not actually field element, which is what happens when you reach for internal functions like field reduce ones, and defeat the type safety. I should have maybe put this in as a separate package. That would not have happened. But anyway, back to where we were. Boring SSL just does a %. I'm going to write it like that just to make progress, and then leave a comment about it. All right, that that should work. Let's crawl our way back up. We wanted this because we wanted reject bounded poly here, and that was here. We've done our absorb, and then we do the while j blah blah blah. We don't do buffered this time, so for j less than n, we squeeze a single byte. That's going to be super slow, but also I don't care about key generation that much, but also I guess we just have the code, so might as well. Yeah, you're just lying. That's not the rate of 168 136. Oh no, I'm wrong. It actually put the right one in. Oops. Yeah. Okay, so we'll call them Z0 modulo 16, so it's going to be the lower bits. And Z1 is going to be the divided by 16, so shift the right by, yep. If it's different, so if there's no error, we set it and move forward, and we do it for each of them. Just like here, we have to do a if j so let's just move the exit to a single place, and then Z1 is the second one and goes into AJ afterwards. Okay, I think this is it. I think we implemented sample bounded poly, which okay, let's make our way back up to where that bounded poly is called. And we need to say passing in and R separately from expandas. Just for the poor reviewer that will have to review this. All right, we've made all our way back up here, so now we can sample S1, and S1 is sampled using row S. So for what does it use? R. Range L. Prev S1 R. Row S. Byte of R. And the parameters looks good. And for R in range PK, why entity inverse? There's no entity so far. There's no entity. Oh, I guess the entity is done right after on S1. But no. S2 R, and the value it's passed in is R plus L. Yep. All right, we've finished this step. The next one is actual math. Well, the little math we talked about. I'm going to take just 1 second to check my phone. Okay. Okay. So we need to entity. Oh, shoot. We did not implement the entity. Oh, I found a code comment in OpenCell 3.6.0 about their implementation of coefficient from health byte, which seems to match boring SSLs. This is not constant time, but will not leak any important info since the value is either chosen or thrown away. No, no, that's an argument for why this can be not constant time. Because either it hits, in which case hits in constant time, like there isn't different time for different values below 14, or it's thrown away, in which case we don't care. But I'm not convinced that this one is safe, because it could be implemented using a lookup table, for example, by the compiler. I'm making it up. In which case it would not be safe. Yeah, no, I can't see it. I'll have to email David Benjamin about this. All right, we need entity and inverse entity to make progress. So let's implement those. Oh God. Okay, it takes in input a polynomial and outputs entity representative. All of this doesn't matter to us. There are 256 values in, 256 values out. And this is a in place algorithm to do it. The datas are hard-coded value. So let's try to structure it the same way, which was like this. We're going to empty it out, but we're going to try to keep the same structure. Zetas are the values. Bit rev 8 of m, well, k, mod q for each index k. And thankfully here too we have a table. Here we go. Wait, k goes from 1 or from 0? Why is this 0? This should be 1. Right? Bit reverse of 0 is 0. Any value elevated to the 0, if I remember correctly, is by convention 1. I mean, I think nothing indexes the 0th one anyway, but this will break tests when I write them. Okay. So. Oh, but haha. But these are not field elements, because these are not in the Montgomery domain. We need to move them all into the Montgomery domain. Time for some Python. Okay. To go to the Montgomery domain, we need to multiply by R and do modulo Q. X times R percent Q. Just to make sure we have it right, let's try to do R in the Montgomery domain. Yeah, that's the right value. Now we take thetas. Uh, Here we go. Okay. So we have zetas. Hopefully they're right. I'm kidding, I'm gonna copy the test, fine. Uh, so bit reverse 8, we probably don't need this part. And I think this is gonna be a 7. Wait. I don't remember what this was. Let's see if it can write it for me. Yeah, that's not helpful. This looks more like it. Oh, because bit reverse moves the bits from in out. Yeah, it's a hateful thing. Okay, and we can do it like I was doing it by doing this instead. Okay, and then we have to find this constant here. Hopefully it's in parameters, perimeter set. The root of unity, there it is. Bit rev 8. Let's try it. Build failed. Right, the code is almost certainly broken all over the place, so... Wait, where is it broken? Uh, no! Montgomery domain. Right, bringing it into the Montgomery domain. Let's instead do got from Montgomery data. Ha! 0 expected 1. Uh, Knew it. Oh. Oh, because it has to be 1 in the Montgomery domain. Um, Woo! Okay. Okay. Oh! OpenSSL does do the mod 5 operation constant time. Hacker's Delight has a similar formula, but with 32-bit representations and the magic number that is some. Okay. Okay, let's try to reverse engineer. Uh, uh, oh, the shift right is has probably a different priority, right? Uh, okay. Let's see if it works. We need it applied from 0 to 14. So list. So mod 5x for x in range 15. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. It works. Because it goes in this direction. And it works for all the values we care about, which, yep. I'm gonna leave that there, if nothing else, to remember to file this with boring SSL. David Benjamin will forgive me. Hey, bird in the ground, will forgive me for having found this on stream. This is a bit awkward. Shoot. Oh well. Also, I think I can see how that happened. It declassifies the int, which disables the constant time checking to do the comparison, but then it's declassified also for that. Oh, Go also has that transformation. Maybe. That's also possible. Maybe value barrier helps here. Who knows? Anyway, we're gonna ask them and then replace this comment. Cool. We were doing the entity. We have the zetas now, so we can do the entity mapping. The entity mapping is essentially just a matter of porting this function one to one. So it starts by making a copy, but I think that instead we do it. Oh no, we also do it in place. Oh, because these are passed by value. So every time we pass them, we're copying them. So this is already a copy of whatever we passed in. So this part we can skip. M0 len 128. Zero len 128, while len is greater or equal than 1. And then len is divided by 2. So this is the same. Greater or equal 1. Len starts at 128. Okay, so we've done all this part. We need to do this part. Start at 0, while start is less than 256. And then start is 2 plus 2 times len. Okay, so also this part is the same. We just need to implement this part. N is plus plus. We got a zeta after. Why does that spec have a... Okay. That one has a thing that starts at 1 and there's... Okay. Zeta's M. And then for J from start to start plus len minus 1. Oh, and this was the trick. I was already reslicing flen, which is the one with len added. Anyway, this loop does from start to start plus len minus 1, so it needs to essentially go from 0 to len. Yes. And then t is the multiplication of zeta, yeah, and w, which is our f, so in this case f len because it's adding len, indexed by j, so this one is the same. Poi f len j is set to the subtraction modulo q of fj, yes, minus t. I think I had already gone out of my way to make the bounds checks go away. And then fj is the addition of fj and t. Okay, it's all the same. Field mall. They're all already in the Montgomery domain, so we can just do field Montgomery mall. I'll be damned. The bound checks eliminations actually work. There's one here and one here, unavoidable, and then there's only that one, which I think we have anyway with the different K instead of M here. Toggle compiler transition details. Yep, that's Zeta's one. The compiler is not smart enough to see that we never overflow here, but it's fine. Okay, so this should be entity. Now let's do inverse entity. Thank you. Bye. So modus reminder in the turn to our inverses and modify. So multiplying any multiple of 6 doesn't change the reminder. Okay. 16 is 1 mod 5. So any division by it doesn't alter the modulus. Okay. From Acker's Delight. Nice. All right. Same, but with potatoes. Actually not. This looks a little different. Okay, so make a copy. Okay. That starts at 256 instead. Len that starts at 1. Sure, why not? Len that goes up to 256. Every time by multiplying by 2. Okay. Starts at 0 and it goes to 256. And every time it becomes plus 2 times len. Yep. Then zetas m minus 1 before, which again annoying little discrepancy. Wait, was it 127? Yeah. Okay. Well, now it's 256. Z is negative zetas m, but that no, we're not going to do a negation here. That would be wasteful. Let's just keep in mind that we need to flip this around. Then same thing with sometimes indexing by plus len and sometimes not. So we have this one that starts as start and this one that starts as start plus len. It goes from start to start plus len minus 1, so j goes to len, that's the same. T is just fj. Yep. Then fj is t plus flen. This one is the same. And then flen is this sequence here, which is t so I'm going to, so it's t let's spell it out. T minus flen j, and then z times that, but also z is negative, so it's actually minus z. So we can probably rewrite this as, yep, and Mary mole sub, what it does is that it does a times b minus c. So z times b minus c. Yep, there we go. This is right. Then we move down here. There's a constant here, which we need to document as 256 to the minus 1 mod q. And for j from 0 to 255, so for all the values in f, in the regional f, not in the subsliced f, yes, we just multiply. But this needs to be in the Montgomery domain. Look at how smaller it is. So we do a field Montgomery multiplication of the thing by that. Okay. I think we have our entity implementation. So it should be len less than 256 instead of len less than or equal. That's entirely possible. While len less than 256. Yes, good catch. Thank you. Yup. Oh, because the other one was starting at 0. No, wait. What does len start at? Len starts at 1 and then less than 256. Oh, okay, because it's not moving. I'm not sure why it's different from the other one, but we are sticking to the spec, and you're right. Sounds good. Okay. Cool. We've got the... Jesus. There. We've got the entity. We can use it. We can use it to do. So this is a matrix multiplication by a vector. And I wrote up those notes partially, so I will also remember how to do it. So matrix by vector multiplication, it produces a vector. To do a matrix by vector multiplication, you go row by row in the matrix, and for each row you multiply every element by the corresponding vector element and add all those products together. Okay, so each result vector element is the dot product, sum of corresponding products of one matrix row by the vector. Okay, sounds good. Which we also already have in ML-Chem somewhere. Where is A? Here. This one. Actually the exact same. Okay. What are we doing here? We're taking a point or two. Yeah, fair enough. We can do these optimizations later. Okay, so we've done everything up to here. Now we have to do something similar to that, which is we have to do inverse entity. Okay. Okay. This one, I like it to be... Okay, and we call the output t as well. And I think t is nothing else than the value we're saving here. So let's slice it by doing priv dot t to p dot k. Is it k? Whatever s2 is, which is k. Yeah. Okay. Okay, so we started at priv dot s2, but actually let's do the same trick where s1 here is ns2 here is that. We also get some free bounce checking from that. And T is PK, okay. So it starts by copying that, and then it ranges over the thing it's adding. It's the vector it's multiplying by. It needs to entity j. So S1j. And it adds to T1 the entity multiplication, yeah, of the entity of that. A of I times P dot L. Because each row is that long, yeah, that looks right. Inverse entity. And A here is un minuto. A here is priv.a, although let's do the same trick of reslicing it there. There still is in bounds, which arguably there shouldn't be. Maybe if we fix K and L and we use those instead, it will feel more comfortable with it not having changed, and we'll optimize based on it. It's still doing that. Okay, whatever. Oh well. This one looks very much like something the compiler should be able to remove, but I don't think it's a hot loop. I'm a little curious why we do the entity in line here and in MLChem we don't. Oh, because then we have to pass around T that way. Actually, is this the stupid thing where then signing is going to de-entity it, re-entity it? Yeah, there. And then re-expands it. Okay, let's take a note that we can probably save these in entity form. This is again the silly thing about the semi-expanded key. Hate it. Okay. Folks, I think I'm gonna call it a break for at least 5 minutes. Or honestly, I might actually be running out of steam. What's after this? There's all the rounding stuff, which is entirely new. So I think we can punt this to the next time. and then we'll have to actually do the encoding for this part. Although not for this part, because as we said, it's just a deeply silly encoding format. Okay. Yeah, I think this is for the next stream. Folks, if you have questions, now is a good time. In the meantime, I'm going to push this code to at least have it saved somewhere. While I wait for any questions. I didn't like that it changed the layout. Let's check that all the tests pass. Yup. JJ. Part of key generation. I'm going to mail them as work in progress, just so I don't lose them. Yeah, makes sense if we do that. Let's see if I can convince it to. I don't know if this is secret stuff. I think not, because you're not going to get the actual secret, which is returned from... No, I think this is not secret. Hopefully it will not print the return value. It did not print the actual secret that was returned. Good. All right, pushed. Folks, if there's no question, see you for the next stream. We'll try to finish this one. Also, now I'm gonna go get cinnamon tea, apparently, in the other room, and email David Benjamin and apologize for dropping this on stream. Bye. Thank you for your company and for catching bags every time somebody catches bags. Love it.